In 1974, I recall us directing a radio telescope toward the star cluster M13, and we sent out mankind's inaugural deliberate communication to extraterrestrial beings. The act was largely symbolic. M13 is situated 25,000 light-years from us. However, what I did not anticipate were the nearer inhabitants who could have been eavesdropping on our unintentional transmissions. Truly, for 123 years, our species has been communicating with the cosmos without any formal consent. Every broadcast of a baseball game, every sitcom transmission, every pulse from planetary radar, all of it seeping into the void, which has formed a growing sphere of human conversation. Subsequently, commencing in 2017, enigmatic interstellar objects started to frequent our solar system with escalating regularity. Oumuamua, Borisov, and now 3I Atlas, with each one proving more peculiar than its predecessor. What if our centuries' worth of electromagnetic noise at last found an audience? What if these are not naturally occurring events, but rather the cosmos's method of acknowledging our communication? I urge you to remain until the conclusion to learn how our cosmic dialogues might at last be receiving responses. Now, I must ask you to ready yourselves. We are commencing part 1, Shouting into the Void. For more than a century, our species has been speaking to the cosmos. Not as a matter of choice precisely, but speaking all the same. Every AM radio station that broadcast baseball games into the evening. Every television tower that beamed sitcoms toward the heavens. Every planetary radar pulse I directed at Venus or some stray asteroid. All of this has bled into space at the speed of light, generating a widening bubble of human chatter that presently stretches approximately 130 light-years from Earth. I refer to this phenomenon as our radio bubble, an orb of electromagnetic interference that signals our existence to any potential listeners. Yet, there are two varieties of calls I have issued into the blackness. The first are inadvertent. Radio leakage. The unintended overflow from a civilization that mastered the manipulation of the spectrum before we understood how to be discreet about it. The second variety consists of purposeful messages in bottles cast into an ocean whose depths I can barely comprehend. During 1972 and 1973, we launched Pioneer 10 and 11, each bearing golden plaques that depicted unclothed humans and indicated our position within the galaxy. It was an optimistic, perhaps naive gesture. The plaques illustrated the hydrogen atom's spin-flip transition, offering a universal measure of time and distance. They charted our solar system and identified Earth as the third planet from a star of medium size. Most daringly, they featured images of a man and a woman standing next to the spacecraft for scale, their hands upraised in what I hoped would be a universal sign of greeting. The Voyager Golden Records came after in 1977, representing a more ambitious endeavor. Chuck Berry's Johnny B. Good now spins through interstellar space, accompanied by whale songs and salutations in 55 languages. The records held 116 images that displayed the variety of life and culture on Earth, along with mathematical and physical definitions, the solar system, the structure of DNA, human anatomy, conception, birth, family units, architecture, art, and music. Carl Sagan described it as a message to the universe. Others labeled it cosmic graffiti. But the most targeted shout originated from Arecibo in 1974. Frank Drake and his team pointed the massive dish at the globular cluster M13 and transmitted precisely 1,679 bits of information. Why 1,679? Because it is the product of two prime numbers, 23 times 73. Anyone who received it would identify this mathematical clue and organize the bits into a rectangular grid. The message would then manifest as a pixelated diagram that showed our numbering system, the structure of DNA, a basic human form, and our solar system with Earth highlighted. The transmission continued for exactly 3 minutes and consumed nearly 1 million watts of power. For those brief moments, Arecibo was the most luminous radio source in our local galactic vicinity. The signal sped toward M13 at the velocity of light, conveying humanity's initial deliberate effort at interstellar communication. It was, in truth, ceremonial. M13 is 25,000 light-years distant. By the time my message gets there, human civilization will have experienced several cycles of rise and fall. Yet, we sent it regardless, because at times the act of calling out is more significant than the anticipation of a response. Giuseppe Cocconi and Philip Morrison had already laid out the logic for us in 1959. In a Nature article, they contended that radio waves would be the common medium for communication between stars. They highlighted the water hole, that tranquil portion of the spectrum between 1.42 and 1.66 gigahertz, defined by the emission lines of hydrogen and the hydroxyl radical, OH, the fundamental components of water. Any civilization that grasped chemistry would know to search there. The hydrogen line at 1,420.4 MHz took on special importance. This frequency corresponds to the energy differential when a hydrogen atom's electron inverts its spin from parallel to antiparallel alignment with the proton's magnetic field. It is the universe's most plentiful element, undergoing its most basic transition. If extraterrestrials sought to create a universal communication standard, the signature of hydrogen would be the clear choice. My own searches have adhered to this line of reasoning for decades. The SETI Institute's receivers scan the hydrogen line. Breakthrough. Listen monitors millions of stars over a multitude of frequencies. The logic is sound. If you wish to be heard across the vastness of interstellar space, you broadcast where the galaxy is naturally quiet. But here is what I have discovered about our own transmissions. They are remarkably difficult to detect. Most of my television and radio signals, after they penetrate Earth's atmosphere, become indistinguishable from background interference within a few light years. The inverse square law is relentless. If you double the distance, the signal strength is reduced to a quarter. Only our most potent transmissions manage to complete the journey to adjacent stars. Planetary radar systems, like Arecibo's S-band transmitter or Goldstone's X-band array, are bright enough to be detected across interstellar distances. These systems, which I designed for mapping asteroids and planets, unintentionally act as lighthouses. Their beams scan the cosmos with each rotation of Earth, producing a distinct signature that would be undeniable to any civilization observing our sector of space. The Deep Space Network stands as humanity's most advanced attempt at a cosmic communication infrastructure. 3 enormous antenna complexes in California's Mojave Desert, near Madrid, Spain, and outside Canberra, Australia, sustain uninterrupted contact with our robotic probes distributed across the solar system. These dishes, some as wide as 70 meters, could be detected by an alien radio telescope from the edge of known space. To such an observer, our spectrum would appear unusual. Narrow carriers would materialize and vanish as our planet turns. The structured broadcasts of FM radio and television, with each channel occupying its assigned frequency slot. Brief, powerful radar pulses sweeping the sky in consistent patterns. All of this would be concentrated around a small blue planet that seems exceptionally active in the radio bands. The International Telecommunication Union safeguards certain frequencies for radio astronomy, acknowledging that some bands must be kept clear for us to listen to the universe. Radio quiet zones surrounding major observatories limit terrestrial transmissions that could disrupt sensitive receivers. The National Radio Quiet Zone in West Virginia covers 13,000 square miles, establishing an oasis of electromagnetic quietude around the Green Bank Observatory. The United Nations Office for Outer Space Affairs orchestrates international space policy, although it has never needed to manage incoming correspondence. Its charter addresses the peaceful utilization of outer space. However, the existing frameworks presuppose human agents functioning under terrestrial legal structures. No one has given serious thought to how international law might be applied to visitors from other star systems. This brings me to a basic conflict within the SETI community. Traditional SETI has consistently been about listening. Passive reception. Breakthrough Listen analyzes petabytes of data from radio telescopes globally, searching for patterns that do not belong. The SETI Institute runs the Allen Telescope Array in Northern California, where 42 dishes collaborate to scan the stars for artificial signals. Yet there is another faction, Active SETI, also known as METI, Messaging Extraterrestrial Intelligence. These scientists wish to transmit powerful, intentional messages into space. They maintain that if everyone merely listens, no one will ever hear anything. The galaxy could be teeming with civilizations, all waiting silently for another to initiate contact. Their proposals bring up unsettling questions. Export control regulations classify high-power transmitters as potential weapons. Radio systems with interstellar communication capabilities could, in theory, be adapted for military use. And then there is the more profound philosophical issue. Who granted us the authority to speak on behalf of Earth? Should such critical decisions be made by small circles of scientists and engineers? The history of false alarms ensures everyone remains cautious. In 1967, Jocelyn Bell Burnell found an exceptionally regular radio signal from space, a pulse every 1.337 seconds, as precise as an atomic clock. The Cambridge team briefly entertained the idea of alien intelligence. They even dubbed it LGM-1 for Little Green Men 1. The Discovery team considered whether they were observing proof of a galactic civilization. It proved to be the first known pulsar, a rotating neutron star whose radio beam swept past Earth like that of a lighthouse. The precision was not artificial intelligence. It was physics operating at extremes that push matter to its limits. Neutron stars contain more mass than the Sun within a sphere barely 20 kilometers in diameter. Their magnetic fields are trillions of times more powerful than Earth's. When such objects spin rapidly, they form cosmic beacons of remarkable regularity. Then there is the renowned WOW signal, detected by the Big Ear Radio Observatory in 1977. For 72 seconds, the telescope registered an incredibly powerful narrowband transmission near the hydrogen line. The signal was so remarkable that astronomer Jerry Ehman scrawled "Wow" in the margins of the computer printout. The transmission exhibited characteristics that SETI researchers had long anticipated for artificial signals: narrow bandwidth, high intensity, and frequency alignment with hydrogen's natural emission line. Despite decades of subsequent observations, I have never detected it again. Theories are plentiful. A singular transmission from an alien civilization, a reflection of an Earth signal off space debris, or some undiscovered natural phenomenon. The signal continues to be one of SETI's greatest enigmas, but also a cautionary story about the difficulties of separating artificial signals from cosmic interference. These experiences taught us important lessons. Extraordinary claims demand extraordinary evidence. Any potential signal must be repeatable, detectable by multiple observatories, and verifiably of extraterrestrial origin. The field has established strict protocols for verification and announcement, designed to stop false alarms from causing global panic or eroding scientific credibility. The Rio scale, analogous to the Richter scale for earthquakes, offers a framework for assessing the importance of potential SETI detections. Ratings from 0 to 10 take into account both the signal's seeming artificial nature and its potential effect on human civilization. Most candidates receive a score between 1 and 3. Intriguing, but not definitive. A confirmed signal from an advanced alien civilization would be rated an 8 or 9, signifying one of the most significant discoveries in human history. Popular culture has influenced our expectations as well. From Orson Welles' War of the Worlds, broadcast in 1938, to modern films like Contact and Arrival, we have been practicing first contact scenarios for generations. These narratives affect how I think about the search, fostering both hopes and fears that may not align with reality. Science fiction often depicts alien contact as dramatic and instantaneous, massive ships materializing in Earth's skies, or powerful signals that transform human society in an instant. But real SETI concentrates on more subtle possibilities: faint signals from distant civilizations, archaeological signs of ancient visitors, or technological artifacts drifting through interstellar space. But here is the reality of shouting into the void. Eventually, you begin to question if anyone is listening. I have been broadcasting for over a century now. My radio bubble continues to grow, carrying the sounds of human civilization to nearby stars. Each year, our electromagnetic signature extends to new solar systems, announcing our presence to potential observers. If someone out there has been paying attention, if they picked up our first television broadcasts, our radar pulses, our intentional messages, they would have had decades to formulate a reply. The physics are simple. Signals move at the speed of light. Therefore, responses from nearby stars would arrive within decades of our initial transmissions. The question that keeps me, as a SETI scientist, awake at night is not whether intelligent life exists in the universe. Statistical arguments indicate the galaxy should be abundant with civilizations. The question is more straightforward and, in a way, more unsettling. What if someone has finally answered? Part 2. The First Response Night and the Genesis of 3I Atlas. On July 1, 2025, the Atlas telescope at Rio Hurtado, Chile, was performing its primary function, surveying the southern celestial hemisphere for any object that traveled with excessive speed or possessed unusual luminosity. The Asteroid Terrestrial Impact Last Alert System runs 4 robotic observatories, their cameras capturing images throughout the night, compiling a catalog of every rock that could pose a threat to Earth. Atlas is at the forefront of automated sky surveillance. Each observatory takes pictures every 30 seconds, covering vast areas of the sky with each shot. Advanced algorithms compare sequential images, identifying objects that move relative to the stellar background or exhibit abnormal brightness fluctuations. The system was conceived to find potentially dangerous asteroids weeks or months prior to impact, affording humanity the time to react to cosmic dangers. At 3:42 UTC, the automated detection system of Atlas IV flagged an unusual object in the constellation Microscopium. It was a point of light moving against the stellar backdrop at a rate of nearly 3 arcseconds per hour. This was fast, quicker than any asteroid ought to move at that distance. The object was already within Jupiter's orbit and approaching the inner solar system. The detection algorithms immediately started to compute preliminary orbital parameters. The object's position and velocity pointed to a trajectory unlike any recorded in the asteroid catalogs. Initial calculations suggested an eccentricity exceeding 1, the mathematical hallmark of an unbound orbit. This was not gravitationally captured material from the asteroid belt. This was an object from interstellar space. Within 6 hours, Pan-STARRS in Hawaii and the Zwicky Transient Facility in California provided confirmation. The object was genuine, it was swift, and its trajectory was impossible for any natural inhabitant of our solar system. 3 separate observatory systems had identified the same anomalous moving object, which ruled out the chance of instrumental malfunction or cosmic rays striking the detectors. The Minor Planet Center in Cambridge, Massachusetts, acts as the global hub for discoveries of asteroids and comets. Their computers processed the object's orbital elements and reached a disquieting conclusion: an eccentricity of 1.47, signifying a hyperbolic excess velocity of approximately 15 kilometers per second. This was not tethered to our sun. This was an interstellar visitor on a hyperbolic path that would take it through our solar system and then back out into the galaxy. The discovery set off immediate follow-up observations from major observatories across the globe. The European Southern Observatory's Very Large Telescope in Chile started to track the object with its 4 8.2-meter mirrors operating in unison. The Keck Observatory in Hawaii entered the campaign, employing adaptive optics to obtain diffraction-limited imagery. The Hubble Space Telescope was granted emergency scheduling to observe this uncommon interstellar visitor. The designation was assigned quickly: 3I Atlas. The 3I indicated it was the third confirmed interstellar object, after 1 Oumuamua in 2017 and 2I Borisov in 2019. The Atlas suffix paid tribute to the discovering observatory, in line with the tradition of acknowledging the initial detector of important astronomical objects. But 3i was distinct from its forerunners. It was larger, brighter, and moved in a manner that did not quite align with conventional physics. Oumuamua had been a tumbling, elongated rock about the size of a city block. Its light curve pointed to an extreme geometry, with a length at least 5 times its width, and possibly much greater. The object reflected sunlight in an odd way, displaying properties unlike any known asteroid or comet. Most perplexingly, it exhibited signs of non-gravitational acceleration, slight pushes that could not be attributed to the sun's gravity alone. Marco Micheli's team at the European Space Agency had meticulously analyzed Oumuamua's trajectory using data from the Hubble Space Telescope and ground-based observatories. Their 2018 Nature paper documented systematic deviations from purely gravitational motion. The accelerations were minor but statistically significant, about 5 times 10 to the negative 6 meters per second squared, roughly 10,000 times weaker than Earth's surface gravity, but undeniably real. Some of my colleagues proposed outgassing, similar to a comet, but without a visible tail. The accelerations could be due to sublimating ice, which would create small rocket-like effects as the object warmed near the sun. Others put forward more exotic theories. A piece of an alien light sail propelled by stellar radiation pressure, or debris from a disrupted comet with an unusual composition. 2i Borisov acted more predictably. It was a proper comet from interstellar space, featuring a fuzzy coma and a distinct tail that was visible to ground-based telescopes. It adhered to the physics textbooks perfectly, which reassured astronomers that most interstellar objects would be natural, albeit rare. Borisov's composition was very similar to that of solar system comets: water ice, carbon monoxide, and organic compounds sublimating as it neared the sun. 3i Atlas landed somewhere between these two extremes, and that is what made it scientifically captivating and potentially alarming. Initial photometry showed a light curve unlike any in the catalogs. Most asteroids tumble erratically, their brightness changing as different surfaces catch the sunlight. This tumbling is a result of their collision history, impacts that set objects spinning in complex rotational states. However, 3i exhibited quasi-periodic modulation, regular variations that indicated it was rotating in a controlled, almost mechanical fashion. The light curve displayed primary variations with a period of about 7.3 hours. But nested within that cycle were secondary oscillations that suggested a complex geometry or surface features. Most fascinatingly, the periods remained remarkably stable over weeks of observation. Natural tumblers usually show period variations as their rotational states change due to various torques, but 3i kept consistent timing, as if something was managing the object's orientation. Spectroscopic observations from the European Southern Observatory uncovered more mysteries. The object displayed subdued outgassing signatures despite its close pass to the sun. Most comets develop characteristic spectral features, emission lines from sublimating water, carbon monoxide, and other volatiles. But 3i's spectrum was exceptionally clean, consisting mainly of reflected sunlight with only faint indications of gas emissions. The reflectance spectrum did not correspond to any known type of asteroid or comet. The colors were off, too red for typical silicate materials, yet not matching organic-rich objects. Absorption features suggested surface materials that might be uncommon or artificially treated. Some spectroscopists hypothesized exotic carbon compounds, or even metallic films that could create such unusual optical properties. Radio astronomers at Goldstone attempted to paint the object with their planetary radar system. The 70-meter Deep Space Network antenna sent out powerful pulses at 8.56 gigahertz, the same frequency I used to map Venus and track near-Earth asteroids. The return signal was faint, but fascinating. Instead of the rough, scattered echo typical of an asteroid's irregular surface, 3i Atlas yielded specular reflections, flat, mirror-like returns that pointed to smooth surfaces positioned at specific angles. The radar cross-section was smaller than anticipated for an object of its optical brightness, suggesting either an unusual composition or a geometry that dispersed radio waves in unforeseen ways. When the James Webb Space Telescope directed its infrared eye at 3I, the data grew even more peculiar. JWST's unmatched sensitivity uncovered thermal properties that were hard to explain simply. The object's thermal signature suggested a low albedo. It absorbed most of the sunlight that struck it, as one would expect from a dark, potentially organic-rich surface. Yet, embedded within this thermal radiation were high-intensity specular spikes, narrow beams of reflected infrared light that materialized and vanished as the object rotated. This pattern was consistent with thin film structures, or engineered coatings, that could reflect light at certain wavelengths while absorbing others. Natural materials rarely exhibit such selective optical characteristics. Ground-based observatories in Chile synchronized their observations, leveraging the Southern Hemisphere's superior viewing geometry. The object was set to remain visible through December 2025, providing astronomers a valuable opportunity to study humanity's third interstellar visitor. The Atacama Large Millimeter-Submillimeter Array joined the effort, searching for molecular emissions that could reveal the object's composition and internal structure. The discovery sparked intense scientific interest, but was communicated to the public with careful management. Space agencies had learned from the Oumuamua incident, where speculative theories about alien technology had dominated media coverage before thorough scientific analysis was finished. Press releases highlighted the object's interstellar origin and unusual traits, while steering clear of premature speculation about artificial origins. However, it was the radio observations that elevated scientific interest into a state bordering on consternation. On the 15th of July, 2 weeks after the discovery, radio telescopes at various locations detected a faint, narrowband carrier signal that appeared to be co-moving with 3I Atlas. The frequency was approximately 1,420.4 MHz, just slightly off from the hydrogen line, the universe's most significant radio frequency and the traditional focus of SETI searches. The detection was made simultaneously by the Very Large Array in New Mexico, the Green Bank Telescope in West Virginia, and FAST in China. Independent observations from different continents ruled out the possibility of local interference or instrumental errors. The signal was real. It was of extraterrestrial origin, and it seemed to be emanating from humanity's third interstellar visitor. Radio frequency interference is the curse of radio astronomy. Satellite transmissions, cell phone towers, and even microwave ovens can taint observations with spurious signals that resemble astronomical phenomena. But this signal cleared every test for extraterrestrial origin. It was present only when antennas were aimed at 3I Atlas. It Doppler shifted in perfect harmony with the object's movement. It maintained consistent intensity and frequency traits across numerous observing sessions. The signal initially showed no discernible modulation, just a clean, narrowband tone that drifted in frequency as 3I Atlas traversed space. The Doppler shift confirmed that the source was moving with the object, not stationary somewhere in the background sky. The frequency stability was exceptional, hinting at a highly advanced oscillator locked to atomic frequency standards. The scientific community's first response was one of cautious disbelief. Extraordinary claims demand extraordinary evidence. Natural phenomena can sometimes generate narrowband radio emissions, such as pulsars, masers, and plasma interactions in planetary magnetospheres. But the frequency was suspect. Why broadcast so near the hydrogen line unless you intended to be heard by astronomers who knew where to search? But as confirmations arrived from observatories all over the world, an unsettling possibility began to take shape. 3I Atlas was broadcasting deliberately. The press naturally showed no such caution. Despite careful classification by government agencies, information about the radio detection leaked out within hours. Social media was set ablaze with speculation. The hashtag #TheReply started trending on Twitter. YouTube videos with titles like "Proof, Aliens Answer Our Call" amassed millions of views. The object that I, as an astronomer, called 3I Atlas, was given a dozen informal names. The messenger, the reply, Visitor 1. Amateur radio operators across the globe started to monitor the hydrogen line frequency, hoping to detect the signal for themselves. Software-defined radio systems, which were inexpensive and widely accessible, enabled thousands of listeners to join the observations. The democratic aspect of radio astronomy meant that the discovery could not be concealed or controlled by official bodies. I and my colleagues tried to keep things in perspective. The signal might be natural, some unknown plasma phenomenon, or an exotic interaction between the object and the solar wind. Radio emissions from comets were not unheard of, though they usually happened at different frequencies and had different characteristics. The proximity to the hydrogen line frequency might be a coincidence rather than intentional. Government space agencies released careful statements that stressed the preliminary nature of the observations. NASA's press releases were strictly factual: trajectory, size estimates, orbital evolution, radio detection. They refrained from speculating about artificial origins, although internal communications suggested a different story. Behind closed doors, planetary defense coordinators were posing difficult questions about objects that could maneuver and communicate. The Planetary Defense Coordination Office, formed after the Chelyabinsk meteor impact in 2013, had concentrated on natural threats, asteroids and comets that could collide with Earth. But 3I Atlas introduced a new type of concern. How do you evaluate the threat level of an object that might be under intelligent control? The name 3I Atlas was retained in official use, but the public imagination preferred more descriptive labels. The reply captured something fundamental about humanity's collective psyche. We had been calling out into the void for over a century with radio signals, television broadcasts, and deliberate messages like the Arecibo transmission. Now it seemed someone had finally called back. The premise of what was to come was both simple and profound. For the first time in human history, we would investigate the possibility that an interstellar visitor was not merely a cosmic chance event, but an answer, a response to our own transmissions into space. Every observation, every measurement, every analysis would be carried out with strict scientific standards, yet guided by one central question. What if 3I Atlas heard us calling and chose to call back? The implications, if true, would redefine every assumption I had about my place in the universe. We were not alone. Someone was listening. And they had journeyed across the galaxy to inform us that they had heard our voice among the stars. But first, I had to ascertain whether we were contending with an extraordinary natural phenomenon or something entirely different. Something that had traversed the interstellar void with the specific purpose of finding us, bearing a message we were only just starting to decipher. Part 3. A wave of visitors, not a one-off. 3I Atlas was not an isolated case. 3 weeks after its initial discovery, automated sky surveys started to identify additional fast-moving objects on hyperbolic trajectories. The detection pattern pointed to something unparalleled in the annals of astronomy. Multiple interstellar visitors arriving within months of each other. Their appearance was coordinated in ways that defied every assumption about random cosmic occurrences. 4I was found in data from the Catalina Sky Survey on the 22nd of July, 2025. The Lincoln Near-Earth Asteroid Research Program detected 5I 2 days later. By August, amateur astronomers using backyard telescopes were adding to a burgeoning catalog of interstellar visitors. Their findings were confirmed by professional observatories that operated telescopes costing hundreds of millions of dollars. These were not random pieces of cosmic debris flung out by some distant stellar event. The objects had common characteristics that grew more unsettling with each new discovery. Firstly, there were their approach vectors. A statistical analysis of interstellar object trajectories should reveal a random distribution, with objects coming from all directions as they move through the galaxy's gravitational field. But this group exhibited a loose coordination that was off by orders of magnitude from what was expected. Their trajectories all originated from a cone of sky roughly 15 degrees wide, centered on the constellation Lyra, as if they had all been dispatched from the same general area of space. Dr. Alan Fitzsimmons at Queen's University Belfast was in charge of the statistical analysis. His team determined that the probability of such coordination happening by chance was about 1 in 50 million, far below the threshold for claiming statistical significance in any other area of astronomy. Something had directed these objects toward our solar system with a precision that suggested intelligence and sophisticated technology. More disturbingly, their perihelia, the points of closest approach to the Sun, were all within a tight range of distances between 0.8 and 1.2 astronomical units. They were threading the needle of Earth's orbital zone, passing through the area where our planet orbits the Sun. The accuracy of their targeting was remarkable, hinting at a knowledge of our solar system's structure and possibly Earth's precise location. The likelihood of natural interstellar objects coincidentally converging on Earth's orbital zone was extremely low. These visitors had been sent to us. Their trajectories had been calculated to optimize observation opportunities from Earth-based telescopes while keeping a safe distance from our planet. Analysis of their light curves revealed further patterns that were inconsistent with natural explanations. While 3I Atlas seemed to be a thin, rotating panel with a controlled orientation, the subsequent objects displayed even more unusual geometries. The brightness variations of 4I indicated a needle-like shape with an aspect ratio approaching 20:1, longer and thinner than any known natural object in the solar system. The photometric data suggested that 4I was tumbling end over end with a period of approximately 3.2 hours. But this tumbling was not erratic, like that of a natural collision fragment. The rotation showed signs of controlled motion, as if internal mechanisms were adjusting the object's orientation for optimal solar energy collection or communication alignment. 5I appeared to be a tumbling fragment, its light curve exhibiting complex variations that suggested a partially broken structure. Spectroscopic analysis pointed to unusual surface properties, with materials that might be porous or partially hollow, leading to optical characteristics unlike any known asteroid or comet composition. A smaller object, designated 6I, produced light curves consistent with what I and my fellow astronomers could only describe as a flake, something thin and flexible, rippling as it moved through space. The brightness variations suggested a sheet-like structure that might be warping under thermal stress or actively altering its shape. These forms contradicted conventional asteroid physics. Natural collision fragments adhere to predictable patterns based on material strength and impact dynamics. Rocky bodies tend to break into roughly spherical pieces. Icy comets fracture along structural weaknesses. But thin film structures, sails, sheets, panels, would behave precisely as the observations indicated. The implications were disconcerting. Natural processes do not typically create objects with extreme aspect ratios and controlled rotational states. However, artificial constructs designed for interstellar travel might exhibit exactly these features, especially if they were designed for minimum mass and maximum surface area. Radio telescopes across the globe coordinated their observations, tracking each object as it neared its perihelion. The findings painted a picture that challenged every assumption about interstellar visitors. Each object emitted narrowband radio signals near the hydrogen line, but the signals were not all the same. They had different modulation patterns, different frequency offsets, and different temporal characteristics. The radio signatures suggested a distributed communication system rather than coincidental emissions. 3I Atlas kept its steady carrier tone at 1,424 MHz. 4I broadcasted at 1,426 MHz with subtle amplitude modulation. 5I transmitted short bursts at various frequencies within the water-hole spectrum. 6I generated complex signals that appeared to carry encoded information in both its frequency and timing variations. The variety of signals ruled out simple explanations based on natural phenomena. Plasma interactions or maser emissions would show similar characteristics across objects with similar compositions and trajectories. But these visitors were broadcasting as if they were part of a coordinated fleet, with each one contributing to a larger communication effort. Dr. Elena Vasquez at the Arecibo Observatory put forward what came to be known as the staging hypothesis. The objects were not arriving randomly or even as debris from a single catastrophic event. They were part of a carefully planned sequence designed to maximize observability and redundancy, while reducing the risk that their message would be missed or dismissed. The staging approach was logical from an engineering standpoint. If you wanted to communicate with a newly discovered technological civilization, sending multiple messengers would increase the chances of success, even if some were missed or misinterpreted. The different characteristics of each object provided various kinds of evidence for artificial origins, making it harder and harder to dismiss the entire group as natural phenomena. The temporal correlations were equally telling. When I and other astronomers reconstructed the launch windows needed for each object to arrive at its observed time, assuming interstellar travel speeds of 10 to 20% of the speed of light, we found links to Earth's broadcast history that seemed too precise to be a coincidence. 3I Atlas, if launched from a star system about 50 light-years away, would have left around 1975, the era of powerful television transmitters and the first major planetary radar campaigns. 4I's timeline matched the early space age and the construction of large military radar installations. 5I corresponded to the time when commercial satellite communications started to fill Earth's spectrum with structured signals. It was as if someone had been listening to our growing radio signature and was responding in sequence. Each probe was launched in response to successive stages in humanity's electromagnetic story. The visitors were not just confirming that they had heard us. They were showing detailed knowledge of our technological progress over several decades. The Atacama Large Millimeter Submillimeter Array in Chile began a coordinated campaign to track the objects with meter-scale precision. VLBI, Very Long Baseline Interferometry, combined data from radio telescopes around the world, creating a virtual dish the size of Earth. The positional accuracy was extraordinary, allowing us to detect tiny course corrections and attitude adjustments that would not be visible to individual observatories. The VLBI results confirmed that several objects were making subtle changes to their trajectories, small alterations in velocity and direction that could not be explained by gravitational perturbations or radiation pressure alone. The course corrections seemed deliberate, adjusting the objects' paths to optimize viewing geometry from Earth or to maintain the quality of their communication links. High-energy astronomy facilities joined the comprehensive monitoring effort. IceCube in Antarctica, designed to detect neutrinos from cosmic events, watched for exotic particle emissions that might be associated with advanced propulsion systems. Air shower arrays looked for correlations between the object's positions and high-energy cosmic ray detections. The results from high-energy observations were disputed and controversial. Some researchers claim to have found faint but statistically significant correlations between the visitors' positions and neutrino or cosmic ray events. Others found no such correlations and attributed the claims to statistical fluctuations or systematic biases in the analysis. The debate reflected deeper uncertainties about what technologies the visitors might be employing. Conventional chemical or nuclear propulsion would leave no detectable signature at interstellar distances. But more exotic possibilities, antimatter engines, fusion ramjets, or entirely unknown physics, might produce high-energy particles that Earth-based detectors could observe. Citizen science mobilized with unprecedented speed and scale. The Zooniverse platform launched Interstellar Visitors, allowing volunteers worldwide to classify light curves and radio spectrograms. Within weeks, hundreds of thousands of participants were contributing to the analysis. Their collective effort represented person-years of labor that would have been impossible for professional astronomers alone. Community-flagged anomalies often led to priority observations at major observatories. Amateur astronomers discovered subtle variations in signal timing that professional automated systems had missed. High school students identified patterns in radio emissions that suggested encoding schemes more sophisticated than simple carrier tones. The collaborative effort represented the largest coordinated scientific response to a single phenomenon in history. Social media platforms became repositories for observational data and analysis tools. GitHub hosted open-source software for signal processing and orbital calculations. The entire global community was participating in humanity's first systematic study of visitors from another star system. Space operators faced more immediate and practical concerns. The object's trajectories took them through heavily traveled regions of the inner solar system. Conjunction bulletins were sent out to satellite operators, warning of close approaches to geostationary orbit and critical spacecraft assets. The visitors posed no direct collision threat, but their unpredictable maneuvering capabilities raised new categories of operational risk. Insurance companies began reassessing their models for space debris collisions and communications interference. What if these visitors were not entirely predictable? What if they could maneuver more aggressively than currently observed? The possibility of technology beyond human understanding introduced new variables into actuarial calculations that had traditionally focused on natural hazards and human error. The public's reaction swung between wonder and anxiety as more visitors appeared throughout the summer and fall of 2025. Astronomical societies reported record attendance at star parties and observatory open houses. But the same crowds that gathered to glimpse the visitors through telescopes also reflected deeper uncertainties about humanity's place in a universe that suddenly seemed much more crowded. Social media buzzed with theories ranging from rigorous scientific speculation to apocalyptic prophecy. Financial markets showed unusual volatility in aerospace and defense stocks as investors tried to gauge the implications of technologies that might be centuries or millennia ahead of human development. Some clearly believed humanity was about to learn something that would change everything. Space tourism companies reported a surge in bookings for suborbital flights, as if getting a little closer to space would provide some advantage when the visitors made their intentions known. Pilgrimage sites formed spontaneously at radio observatories, where visitors could stand near the dishes that were tracking the objects in real time and listen to recordings of their transmissions. The most unsettling aspect was the object's apparent coordination. As more visitors appeared throughout the summer and fall of 2025, their radio emissions began showing temporal correlations that went beyond simple frequency coordination. Brief, synchronized transmissions occurred across multiple objects simultaneously, lasting only seconds but clearly coordinated across millions of kilometers of space. Whatever intelligence had dispatched this flotilla was maintaining active communication between its components. The visitors were not just broadcasting to Earth. They were talking to each other, coordinating their activities in real time despite the vast distances separating them. The implications for their communication technology and organizational sophistication were staggering. By September, the catalog included 15 confirmed interstellar objects, with dozens more candidates awaiting confirmation as their orbits became better determined. The sky was filling with artificial visitors, each one broadcasting its presence on frequencies that we humans had long considered the natural choice for interstellar communication. The pattern was becoming undeniable. These were not random cosmic wanderers or natural debris from some distant stellar catastrophe. This was a planned mission, executed with precision and coordination that spoke to an intelligence and technology far beyond human capabilities. The question was no longer whether someone was trying to communicate with Earth. The question was what they were trying to say and whether we were prepared to listen to a message that might reshape our understanding of intelligence, technology, and our place among the stars. Part 4. A pattern in the noise. Did they hear us specifically? The mathematics were indisputable, and they presented a narrative that left me and my fellow astronomers profoundly uneasy. If the visitors originated from star systems approximately 50 light-years distant, they would have needed to detect Earth's radio emissions decades ago to synchronize their arrival for 2025. This introduced a fundamental question that went to the core of the enigma. When could they have known we were here? Dr. James Chen at MIT's Haystack Radio Observatory undertook the challenge of reconstructing humanity's expanding radio bubble decade by decade. This analysis necessitated a careful examination of transmitter power, antenna patterns, and the inverse square law that dictates signal propagation through space. Not all of our broadcasts were equivalent in terms of their detectability at interstellar distances. Television broadcasting commenced in earnest during the 1940s, but early systems were low power and lacked focus. The signals that escaped into space were feeble and would be challenging to detect beyond a few light years. High-power military radars became widespread during the Cold War, generating stronger signals that could potentially be identified across interstellar distances, but their focused beams swept across the sky in patterns that might make them hard to recognize as artificial. By the 1960s, my most powerful transmissions, planetary radar systems designed to map Venus and track asteroids, were projecting megawatts of radio energy toward specific areas of the sky. These systems operated at frequencies selected for optimal planetary observation, but they also produced the most luminous radio signatures in Earth's history. The Arecibo Observatory, finished in 1963, became humanity's most potent voice in the cosmos. Its 305-meter dish could transmit up to 1 million watts of radio energy in a tightly concentrated beam. When I used it for planetary radar observations, Arecibo generated radio signatures, bright enough to be detected by similar facilities across interstellar distances. The timeline was stark and precise. Any civilization within 50 light years would have picked up our early television signals in the 1970s and 1980s, as those broadcasts finished their journey through interstellar space at the speed of light. Our most powerful radar transmissions would have reached nearby star systems in the 1990s and 2000s, offering clear proof of a technological civilization on Earth. But the visitors were not just appearing at random intervals. Their approach vectors, when traced back through galactic space using advanced orbital mechanics calculations, indicated specific star systems that would have been ideally situated to observe Earth during our most active broadcasting periods. The correlation analysis demanded extreme caution to sidestep the statistical pitfalls that had troubled other searches for patterns in astronomical data. Dr. Sarah Martinez at the Harvard-Smithsonian Center for Astrophysics headed a team that cross-referenced the visitors' origin vectors with Earth's transmission patterns over several decades, employing Monte Carlo simulations to evaluate the likelihood of spurious correlations. HD 164595, a sun-like star 94 light-years away, was directly in the line of our most powerful Arecibo transmissions during the 1970s and 1980s. The alignment was perfect. When Arecibo was aimed at Venus for radar mapping, its beam passed over HD 164595's location in the sky. Any receivers in that system would have detected Earth's radar signals with a clarity that made their artificial origin undeniable. Wolf 359, only 7.9 light-years away, would have received our television signals with exceptional clarity due to its position relative to Earth's rotational axis. The red dwarf star is situated nearly perpendicular to our planet's equatorial plane, which means it would have observed Earth from an angle that maximized the reception of our strongest commercial broadcast transmissions. Tau Ceti, a favored target of SETI searches because of its proximity and sun-like characteristics, lined up perfectly with several major radar campaigns conducted during the 1990s and early 2000s. That star system would have received clear evidence of technological activity on Earth, precisely when our deepest space missions were starting to unveil the structure and composition of our solar system. The statistical analysis showed correlations that were significant at the 4 sigma level, odds of roughly 1 in 15,000 that the patterns were purely coincidental. In particle physics, such correlations would be considered strong evidence for new phenomena. In astronomy, they required serious consideration, even from skeptical researchers. However, critics contended that such analysis was susceptible to what statisticians term the look elsewhere effect. The propensity to discover patterns when you sift through enough data with sufficient flexibility in your analytical methods. With hundreds of nearby star systems and decades of transmission history, some correlations were bound to appear, even if no genuine relationship existed. Dr. Robert Hayes at the University of Arizona spearheaded the skeptical counterargument. His team performed parallel analyses using randomized datasets and slightly different statistical techniques. They discovered that apparent correlations could arise from chance alignments combined with observational biases and the human tendency for pattern recognition. "We're seeing patterns because we want to see them," Hayes asserted in a widely referenced paper in the Astrophysical Journal. Give humans enough data about their own transmissions and some cosmic visitors, and they will find connections between anything. The universe has no obligation to be concerned with our radio broadcasts. Yet, the temporal patterns within the visitor's arrival sequence offered more compelling evidence that transcended simple geometric alignments. The objects did not arrive at random intervals dictated solely by orbital mechanics. Their spacing mirrored key milestones in humanity's broadcast history with a precision that was hard to write off as coincidence. Dr. Lisa Johansson at the SETI Institute put forward the echo hypothesis, a model that regarded each visitor as a reply to specific human transmissions. If the visitors were indeed responses to our broadcasts, their arrival timing should reflect our own transmission milestones, delayed by the light travel time between star systems, plus the time needed for interstellar travel. She developed a mathematical model that assumed interstellar travel velocities of 10 to 20% of the speed of light, fast by my standards, but attainable for civilizations with advanced propulsion technology. The model forecasted visitor arrival times based on the intensity and timing of Earth's most powerful radio transmissions, adjusted for the probability that different star systems could have detected those signals. The correspondence between predicted and observed arrival times was striking. 3i Atlas aligned with the timeline for a response to Earth's television broadcasting peak in the 1970s. 4i matched reactions to early military radar installations. 5i corresponded to the era of commercial satellite communication. The patterns suggested not just intelligence, but an intelligence that had been observing Earth's technological progression over multiple decades. The most convincing evidence came from an information theory analysis of the visitors' radio emissions. Several objects displayed transmission patterns that seemed to allude to the 1974 Arecibo message, that renowned 3-minute broadcast aimed at the globular cluster M13. The Arecibo message had encoded the numbers 1 through 10 in binary notation, followed by the atomic numbers for hydrogen, carbon, nitrogen, oxygen, and phosphorus, the essential elements of DNA. It featured a representation of the double helix structure, a simple pictogram of a human figure, and a diagram of the solar system with Earth identified as the third planet from the Sun. Some of the visitors' signals included similar numerical progressions, but with slight variations that suggested intentional alteration rather than mere repetition or random noise. The binary sequences were identifiable but went beyond the original Arecibo format, incorporating mathematical concepts that humans had discovered but had not yet broadcast into space. The prime number sequences were especially remarkable and possibly represented the strongest proof of deliberate communication. The Arecibo message had employed prime numbers as a universal mathematical concept, something any technological civilization would recognize, irrespective of their specific counting system or mathematical notation. Several visitors broadcast their own prime sequences, 2, 3, 5, 7, 11, 13, 17, 19, 23, but then strayed from the standard progression in ways that appeared deliberate rather than accidental. It was as if someone was saying, "We got your message and understood your mathematical language. Now let us show you variations and extensions that display our own mathematical sophistication." The deviations were not random. They followed patterns that matched advanced number theory, twin primes, Sophie-Germain primes, Mersenne primes. The visitors were exhibiting mathematical knowledge that went beyond basic arithmetic, showing a familiarity with concepts that human mathematicians had developed over centuries of research. A statistical analysis of the mathematical content required extreme care to avoid the tempting pitfall of finding patterns in noisy data. Dr. Chen's team pre-registered their hypothesis before examining the visitors' transmissions, committing to specific statistical tests and significance thresholds. They used Monte Carlo simulations to assess the probability of discovering apparent mathematical patterns in random data. Even with these strict precautions, the connections remained statistically strong. The likelihood that random radio emissions would contain recognizable mathematical sequences related to human broadcasts was less than 1 in 10,000. The visitors were demonstrating a knowledge of human mathematics and extending it in ways that proved their intelligence and technological advancement. However, the skeptical community pushed back strongly against these interpretations. The debate unfolded in academic journals and on social media with equal fervor, mirroring fundamental disagreements about how to assess extraordinary claims with limited information. Hayes and his colleagues contended that the apparent mathematical content was more a reflection of human psychology than alien communication. Pattern recognition is fundamental to human cognition, they wrote. We evolved to find meaningful signals in noisy environments. When we look at cosmic phenomena through that evolutionary lens, we are prone to see intelligence even in random processes. The statistical arguments grew increasingly complex as both sides refined their methods and assumptions. Proponents of the intelligence hypothesis pointed to multiple independent lines of evidence: geometric correlations, temporal patterns, mathematical content, and coordinated behaviors across multiple objects. Critics highlighted the risks of multiple hypothesis testing and the human inclination to find significance in large data sets. The debate drew the attention of philosophers of science and experts in statistical methodology. The National Academy of Sciences formed a special panel to evaluate the evidence and offer guidance for future research. The panel's initial report was cautiously phrased, but conceded that the visitors represented phenomena deserving of serious scientific investigation using the most rigorous methods available. Social media amplified the controversy with hashtags like Geo pattern or pareidolia trending globally. Late-night talk show hosts joked about humans being so self-absorbed that they assumed every cosmic coincidence was about them. But the scientific community took the analysis seriously, recognizing that even a small chance of intentional contact had enormous implications for humanity's future. The provisional consensus that emerged from months of analysis and intense debate was carefully articulated. The correlations between Earth's transmission history and the visitor's characteristics were statistically significant and not easily accounted for by random processes or observational biases. Whether this constituted intentional communication was still an open question, but the patterns were compelling enough to warrant systematic attempts at a response. The phrase "systematic attempts at a response" carried immense weight. It suggested that we might try to communicate back to see if the visitors would react to our transmissions in real time. The idea was both exhilarating and frightening, my first intentional conversation with intelligence from another star system. After decades of passive listening, we were considering active participation in what could be the galaxy's oldest and most important conversation. The visitors had provided what seemed to be their opening statement, showing knowledge of our mathematics, our history, and our location in space. The question was whether we were prepared to reply and what we might learn from beings who had mastered the art of communication across interstellar distances. Part 5. Anatomy of an Enigma. What 3I Atlas is physically. By October 2025, the collective observations from dozens of observatories worldwide had created the most comprehensive profile of an interstellar object in history. What came to light was a picture that was difficult to categorize. 3I Atlas was approximately 200 meters in its longest dimension, with a width of about 20 meters, and a thickness that radar observation suggested was less than 2 meters. Its aspect ratio was over 10:1, making it one of the most elongated objects ever seen in the solar system. Its form was consistent with a thin panel or a stack of panels, possibly hinged and capable of changing its configuration. The object's non-gravitational accelerations were slight, but undeniable. As it neared its perihelion, small deviations from a purely gravitational path added up to measurable course adjustments. The accelerations were consistent, always directed toward or away from the Sun, never random. They corresponded to the predictions for radiation pressure on a highly reflective surface, but the object's measured albedo was too low to explain such effects. Spectroscopic analysis pointed to a surface chemistry unlike anything in the asteroid catalogs. The spectrum displayed absorption features that were consistent with exotic carbon allotropes, materials that might be engineered rather than naturally formed. There were indications of boron nitride coatings and traces of metals arranged in patterns that suggested deliberate doping for specific electromagnetic properties. The thermal behavior was perhaps the most mystifying aspect. As 3I Atlas moved through different distances from the Sun, its temperature did not follow the simple inverse square law that applies to most solar system objects. Instead, it exhibited thermal plateaus, areas where the temperature stayed almost constant despite changing solar radiation. This pointed to active thermal management, possibly through microlouvers or metamaterial surfaces that could adjust their emissivity in real time. The object's rotation was equally controlled. Unlike natural asteroids, which tumble erratically due to collision history and tidal forces, 3I Atlas kept a stable spin axis aligned with specific celestial coordinates. More fascinatingly, its rotation period showed subtle variations that correlated with solar illumination angles, as if the object was adjusting its orientation to optimize solar energy collection or thermal management. The radio emissions remained the most convincing proof of an artificial origin. The main carrier, at 1,424 MHz, was accompanied by harmonics at precise mathematical intervals. Initially, the signal showed no modulation, just a clean, narrowband tone that Doppler shifted with the object's movement. But as 3I approached its perihelion in November, modulation emerged. The pattern was unmistakable. Prime numbers, groups of pulses corresponding to 2, 3, 5, 7, 11, 13, 17, 19. The sequence went on through the first several dozen primes, and then it repeated. It was the kind of signal that I and other SETI researchers had long predicted as the first communication from an alien intelligence. Mathematically sophisticated, yet simple enough to be recognized as artificial. Dr. Abraham Loeb at Harvard had suggested several criteria for identifying artificial interstellar objects, including unusual brightness at great distances, evidence of artificial acceleration, and electromagnetic emissions. 3I Atlas seemed to meet all of them. Loeb calculated that if the object's reflectivity was normal, its apparent brightness at its discovery distance would require it to generate about 10 gigawatts of internal power, enough to supply a small city. The mainstream astronomical community stayed cautious. Images from the Hubble Space Telescope showed a diffuse coma around 3I Atlas, which was consistent with gas and dust sublimating as the object heated up near the Sun. The astronomy picture of the day featured these images with captions that highlighted normal cometary behavior. Ground-based observations detected water vapor and carbon monoxide in the object's immediate vicinity, which supported natural explanations. However, even normal cometary physics could not fully account for all the observations. The outgassing was too weak to explain the non-gravitational accelerations. The coma's structure had asymmetries that suggested controlled venting rather than simple sublimation. Most perplexingly, the radio emissions continued even when the object was farthest from the Sun, where natural plasma processes should have stopped. The debate centered around competing hypotheses. Natural explanations proposed exotic but plausible scenarios. A fragment from a disrupted comet with an unusual composition and geometry, perhaps containing metallic inclusions that could produce radio emissions through plasma interactions. The controlled rotation and thermal behavior might be due to its internal structure, cavities and chambers that created thermal inertia and gyroscopic stability. Artificial explanations were more speculative, but strangely consistent with the observations. An autonomous probe or messenger system, possibly using solar energy for power and attitude control. The thin geometry suggested a deployable structure, perhaps a communication array designed to maximize its surface area for both solar collection and radio transmission. The prime number sequence pointed not just to intelligence, but to an intelligence that understood human mathematical concepts. A third category emerged, somewhere between natural and artificial. Dr. Elena Rodriguez at the University of Barcelona suggested that 3I Atlas might be technobiotic debris, remnants of a biological civilization that had learned to engineer materials at the molecular level. The object might be partially alive, using biological processes to maintain its structure and behavior across interstellar distances. Risk assessment became a priority as 3I Atlas approached its closest point to Earth in late November. The object was set to pass within 0.3 astronomical units, about 45 million kilometers. Close enough for detailed observation, but far enough to avoid any gravitational disruption of Earth's orbit. A greater concern was the possibility of debris shedding. If the object was indeed artificial and potentially damaged from its long interstellar journey, fragments might break off during its passage around the Sun. The Planetary Defense Coordination Office issued cautious warnings to space agencies worldwide. While 3I Atlas posed no direct collision threat, its behavior was still unpredictable. The controlled accelerations proved that the object could maneuver. The question was whether such maneuvers were automatic responses to solar heating or represented active guidance by some form of intelligence. Companion objects added another layer of complexity. Several smaller pieces, designated 3I Atlas A through 3I Atlas F, traveled in formation with the main object. These fragments showed similar radio emissions and coordinated maneuvers, suggesting they might be calibration mirrors or relay nodes for a distributed communication system. Energy considerations painted a sobering picture. The radio transmissions alone required kilowatts of power, which was substantial for an object with a limited solar collection area. If the emissions were indeed intentional communications, rather than waste energy, they represented a significant investment of resources. Someone or something was expending considerable energy to ensure we could hear them. As 3I Atlas reached its perihelion on the 28th of November, 2025, the astronomical community held its collective breath. This was the moment of closest approach, maximum heating, and if the object was indeed artificial, perhaps maximum activity. Every major observatory on Earth was watching, waiting to see what humanity's most enigmatic visitor would reveal about itself. Part 6. Talking Back, Protocols, Politics, and the First Reply. The moment I and my fellow astronomers confirmed that 3I Atlas was transmitting prime numbers, we faced a question that had never been seriously addressed. How do you reply to a message from space? The International Academy of Astronautics had spent decades creating post-detection protocols for SETI signals. Their guidelines were detailed, but not binding, a cautious framework for verification, analysis, and eventual response that presumed governments would cooperate through existing treaty structures. But no treaty had foreseen visitors that could maneuver and actively communicate while passing through the solar system. The UN Committee on the Peaceful Uses of Outer Space held emergency meetings in Vienna. COPUOS, as it was called, had dealt with everything from space debris to commercial launches, but never interstellar diplomacy. The Committee on Space Research, COSPAR, contributed its expertise on planetary protection protocols, which were originally made to prevent the contamination of Mars and Europa. Did those same principles apply to artificial visitors from other star systems? The International Telecommunication Union had more immediate worries. Radio frequencies were national assets, carefully distributed to prevent interference between terrestrial services. But what happens when an alien intelligence starts broadcasting on frequencies set aside for radio astronomy? The ITU's role in protecting SETI bands suddenly became crucial to preventing interference with humanity's first conversation with the cosmos. Behind closed doors, the discussions were less diplomatic. National space agencies knew that whoever replied first might set a precedent in interstellar communications. NASA's Deep Space Network could reach 3I Atlas with its current equipment. The European Space Agency's ESTRAC network offered similar capabilities. China's growing deep space communication infrastructure was quickly becoming as advanced as Western systems. But the most powerful transmitters were owned by military organizations and academic research institutions. The Arecibo Observatory in Puerto Rico, despite its recent structural failure, had been the world's most powerful radio telescope. Its replacement, the proposed next-generation Arecibo telescope, was still years away. The responsibility had shifted to other facilities. The 500-meter aperture spherical telescope, FAST in China, the upgraded facilities at Goldstone in Canberra, and university-run arrays like the Very Large Array in New Mexico. Dr. Jill Tarter, the former director of the SETI Institute, became an unexpected coordinator. Her decades of experience searching for extraterrestrial signals gave her a unique authority to speak on protocols and procedures. "We've always known this moment might come," she stated in emergency meetings with international colleagues. "The question is whether we respond as one species or as competing nations." The technical hurdles were significant but not insurmountable. Any response to 3I Atlas would need to account for the object's rapid motion and changing distance. Doppler compensation would require precise tracking and real-time frequency adjustments. The transmissions would have to be powerful enough to cross interplanetary distances while remaining narrowband enough to be clearly artificial. The communication protocol was derived from SETI traditions and information theory. We would start with mathematics, the universal language. We would reciprocate the prime number sequence to show comprehension. Then, we would introduce more complex concepts, atomic structures, physical constants, perhaps even a simple star map indicating our position in the galaxy. Content restrictions were a source of intense debate. Military advisors cautioned against disclosing sensitive information about Earth's infrastructure or defensive capabilities. Scientists argued that any civilization capable of interstellar travel would already be aware of our technological limitations. The compromise was elegantly simple. Respond with the same kind of information we had already broadcast deliberately, the mathematical and physical concepts from the 1974 Arecibo message, updated with current knowledge. The modulation scheme had to be simple enough for any intelligence to decode, yet sophisticated enough to convey meaningful information. The team decided on pulse position modulation with strong error correction, slow and inefficient, but highly resistant to corruption. Barker codes would serve as unmistakable preambles, mathematical sequences that could only be artificial. Time was the critical factor. 3I Atlas would be within optimal communication range for only a few weeks. The object's high velocity meant that Earth's rotation would create short communication windows as different antenna complexes came into view. Dynamic scheduling software, originally created for tracking deep space missions, was adapted to maximize contact time with humanity's first interstellar correspondent. Chain of custody protocols were established to ensure that every transmission would be documented and verified. Cryptographic signatures would prevent any later assertions that the messages had been tampered with or fabricated. Multiple observatories would keep independent records, forming a permanent archive of humanity's first intentional communication with another intelligence. The decision to transmit was made on the 3rd of December, 2025. 3I Atlas was nearing its optimal viewing geometry from Earth, and radio astronomers had confirmed that the object's prime number sequence was continuing with increasing complexity. The visitor was demonstrating a mathematical sophistication that went far beyond simple counting. Dr. Martinez initiated the transmission from the Arecibo replacement facility, which was now under international coordination. The message began with the same prime sequence that 3I Atlas had been broadcasting, confirming that we had received and understood. It then presented the first few elements of the periodic table, expressed in binary notation. Next came a simple representation of the hydrogen atom, the very concept that defined the frequency of our conversation. The response arrived 18 minutes later, the light travel time to 3I Atlas and back. The visitor's signal changed. The steady prime number sequence was replaced by a more complex pattern, groups of pulses that corresponded to atomic numbers: hydrogen, helium, lithium, beryllium. But then the sequence deviated from Earth's periodic table, including pulse groups that did not match any known element. It was as if the visitor was teaching us chemistry that we had not yet discovered. Even more remarkable was what happened to the object itself. Ground-based telescopes detected a slight brightening, a brief shutter-like flash that lasted for the exact duration of Earth's transmission. Photometric analysis suggested that part of 3I Atlas had physically reconfigured itself, perhaps by opening reflective panels or adjusting its orientation to create a visual acknowledgement of the radio exchange. The implications were immense. This was not a passive reflection of a natural phenomenon. This was active, real-time communication with an intelligence that could coordinate radio and optical signals across interplanetary distances. News of the successful exchange leaked within hours, despite careful classification. Amateur radio operators worldwide had been monitoring the frequencies, and the distinctive pulse patterns were impossible to conceal. Social media exploded with excitement and speculation. Governments hurried to release statements that emphasized caution and international cooperation, but the fundamental truth was undeniable. Humanity had successfully initiated a conversation with visitors from another star system. The second exchange occurred 2 days later. This time, 3I Atlas initiated the contact, transmitting a more complex mathematical sequence. The pattern seemed to describe orbital mechanics, the motion of objects around gravitational sources. When Earth's mathematicians decoded the full sequence, they realized the visitor was describing not just general orbital theory, but the specific trajectory it was following through our solar system. It was showing us that it understood where it was and where it was going. More importantly, it was demonstrating that its presence in our solar system was not accidental. The trajectory had been calculated, planned, and executed across interstellar distances, with a precision that hinted at technologies humanity could barely conceive. The visitor was not just answering our call. It was explaining how it had heard us, journeyed to find us, and positioned itself for optimal communication. The conversation that ensued would redefine every assumption about our place in the universe and our future among the stars. But first, we had to comprehend what 3I Atlas was attempting to teach us about the galaxy we thought we knew. Part 7. Earth Reacts, Psychology, Faith, Markets. The moment the news of a successful two-way communication with 3I Atlas became public, humanity's collective psyche underwent a transformation that sociologists would spend decades fully comprehending. Mental health hotlines saw a 340% rise in calls in the first week after the exchange was confirmed. The conversations followed predictable themes: existential dread about humanity's position in the cosmos, profound excitement about the future possibilities, and a strange kind of cosmic loneliness, the realization that we had never truly been alone, yet had spent centuries believing we were. Dr. Susan Chen at the Stanford Psychology Institute introduced the term contact syndrome to describe the set of reactions she noticed in her practice. Patients described vivid dreams of space travel, an obsessive tendency to watch the sky, and a sudden feeling that earthly problems had become insignificant. "It's as if people are mentally preparing for a future they can't yet picture," she remarked in her initial research. Religious responses were markedly different across various denominations and faiths. The Vatican released a carefully phrased statement within 48 hours, asserting that the discovery of intelligence beyond Earth was in line with Catholic theology. "The universe is vast and full of wonders," declared Pope Francis. "If God has chosen to populate it with other forms of consciousness, this only enhances our appreciation of His infinite creativity." Evangelical Protestant reactions were more varied. Some leaders welcomed the visitors as proof of God's cosmic reach. Others expressed concern about the theological consequences. Did beings from other worlds have souls? Did Christ's sacrifice apply beyond Earth? Emergency theological conferences were held in seminaries around the world, wrestling with questions that had been purely theoretical until now. Islamic scholars found a more comfortable footing in the Quran's mentions of God's creation extending across multiple worlds. Buddhist leaders viewed the contact as confirmation that consciousness is a fundamental aspect of the universe. Hindu traditions, already at ease with cosmic scales and multiple realms of existence, adapted most readily to the new reality. Financial markets, in the meantime, went through what economists later called the contact correction. Aerospace and defense stocks initially soared, fueled by speculation about new technologies and government contracts. But the gains were short-lived, reversing quickly when early analysis indicated the visitors showed no hostile intentions. Satellite communication companies experienced dramatic shifts in their insurance rates as the possibility of interference, whether intentional or accidental, from advanced alien technology introduced new liability categories. Prices for rare earth elements shot up on speculation that alien technology might depend on exotic materials. Lithium, used in batteries and electronics, doubled in price within a week. Gold, traditionally a safe investment during uncertain times, remained surprisingly stable. It seemed investors believed that beings capable of interstellar travel would be less impressed by shiny metals than past generations of humans had been. The cryptocurrency markets provided a fascinating glimpse into collective psychology. Bitcoin prices surged on theories that decentralized digital currencies might be favored by interstellar traders. New contact coins emerged daily, most of them elaborate scams, but some representing genuine efforts to create communication protocols that could function across species. Information warfare erupted on social media platforms almost instantly. Bot networks, many seemingly state-sponsored, inundated Twitter, Facebook, and TikTok with competing narratives. Some asserted that the entire contact event was a sophisticated hoax orchestrated by world governments to justify increased surveillance. Others insisted the visitors were an invasion force and called for immediate military action. Platform moderators found themselves in the unprecedented role of fact-checking claims about alien intelligence. Twitter's policy team worked feverishly to create guidelines for extraterrestrial content, while simultaneously trying to combat misinformation about the visitors' intentions and abilities. Verification badges started to appear on official observatory accounts, establishing a new class of trusted sources for cosmic news. Educational systems hurried to meet the sudden surge in student interest in astronomy, radio engineering, and astrobiology. Universities saw record enrollment in physics and mathematics programs. Community colleges began offering intensive courses in radio technology, teaching students how to build their own receivers for monitoring interstellar signals. Children's reactions were especially revealing. Teachers noted that students had started to incorporate space themes into their art and creative writing with remarkable sophistication. Many children seemed less taken aback by the contact than adults, as if they had always assumed the universe held other intelligences and were simply waiting for the grown-ups to catch on. The art world responded with its usual fervor. Museums organized impromptu exhibitions of space-themed art. New musical compositions appeared almost daily, many incorporating prime number rhythms or the actual radio frequencies detected from 3i Atlas. Visual artists created installations using the hydrogen line frequency as a central theme. 1,420 MHz translated into colors, patterns, and sculptural forms. Social rituals developed spontaneously. Listen parties became popular, with groups gathering around radios tuned to frequencies where the visitors might broadcast. Astronomy clubs were swamped with new members eager to see the visitors through telescopes. The hashtag #TalkToSpace became a global trend, with millions of people posting messages intended for extraterrestrial audiences. Night sky photography saw a massive surge in popularity. Amateur astronomers who had never owned a camera suddenly purchased telephoto lenses and tracking mounts, hoping to capture images of the interstellar visitors. The photos themselves were unremarkable, distant points of light, indistinguishable from stars. But the act of taking pictures seemed to fulfill a deep human need to document and share this historic moment. Urban light pollution became a political issue for the first time in decades. City councils were pressured to enact dark sky ordinances, dimming unnecessary lighting to enhance astronomical visibility. Hardware stores reported shortages of red flashlights, the preferred lighting for preserving night vision during stargazing. The psychological effects extended into unexpected areas. Marriage proposals reportedly began to include references to the cosmic perspective. Dating apps added views on extraterrestrial contact to their matching algorithms. Pet adoption rates increased, possibly reflecting a desire for companionship in uncertain times. Corporate marketing adapted with remarkable speed. Car commercials showed families driving to remote locations for better sky viewing. Smartphone makers highlighted their cameras' low-light capabilities for astrophotography. Coffee companies sold contact blends for those long nights of sky watching. But perhaps the most significant change was more subtle, a shift in temporal perspective. People started to think on longer timescales, evaluating decisions in the context of cosmic history rather than quarterly profits or election cycles. Urban planning discussions began to include speculation about how cities might need to change for a species that knew it was not alone in the universe. The psychological research would go on for years, but the early patterns were clear. We were not just coming to terms with the existence of other intelligences. We were starting to see ourselves as part of a larger community of minds scattered across the galaxy. The isolation that had defined human consciousness since we first looked up at the stars was, at last, tentatively ending. Part 8. Building a mission in months, not years. By January 2026, the impossible had become unavoidable. We would send a spacecraft to rendezvous with 3I Atlas. The mission plan came together in emergency sessions that united NASA's top engineers, ESA's mission designers, and representatives from commercial space companies that had been quietly transforming access to space. The task was unprecedented, intercepting a target moving at interstellar speeds with a launch window of weeks instead of years. Conventional mission planning operated on development cycles of a decade or more. The Voyager probes took 8 years from concept to launch. The James Webb Space Telescope needed 3 decades from its initial proposal to operation. But 3I Atlas would not wait for human bureaucracy. By mid-2026, the visitor would be accelerating away from the Sun, out of reach of any spacecraft we could realistically build. The answer was to use hardware that was already available or could be quickly adapted. SpaceX's Super Heavy booster, originally intended for Mars missions, could launch significant payloads onto interplanetary trajectories. Solar electric propulsion systems, proven on asteroid missions, could provide the precise navigation needed for an intercept. The challenge was to combine these components into a functional mission in under 8 months. Dr. Robert Braun, formerly of NASA's Jet Propulsion Laboratory, headed the International Mission Design Team. His approach was relentlessly practical. Use only proven technologies, accept greater risks than on normal missions, and concentrate solely on objectives that could be met during a brief flyby. The basic mission profile was elegantly simple. A single large spacecraft would launch in June 2026, following a minimum energy path to intercept 3I Atlas in September. The encounter would last about 6 hours, during which the spacecraft would release multiple small probes designed to approach the visitor from different angles while keeping a safe distance. Guidance, navigation, and control posed the biggest technical hurdles. 3I Atlas was a thin, tumbling target with unpredictable maneuvering abilities. Traditional asteroid flyby missions depended on precise trajectory prediction, but this visitor had already shown it could make small course adjustments. The spacecraft would need autonomous navigation systems that could adapt to the target's movements in real time. The payload selection was driven by urgent scientific priorities. Wideband radio receivers would monitor the full spectrum of emissions from 3I Atlas, looking for communication attempts or information content. Optical cameras with various filters would document the object's physical structure and surface properties. Laser communication systems would try to establish a high-bandwidth link, testing whether the visitor could respond to optical signals as well as radio. Most controversially, the mission included micro-probes, designed for extremely close approaches. potentially within meters of 3I Atlas's surface. These contactors were fitted with sampling systems that could collect material if the chance arose, but their main purpose was detailed observation and active signal transmission from close range. The James Webb Space Telescope's role became vital for the mission's success. JWST's moving target tracking capabilities, though limited to objects moving slower than 75 milliseconds per second, could potentially observe 3I Atlas during certain parts of its trajectory. More importantly, JWST's infrared sensitivity might detect thermal signatures that could reveal its internal structure or energy sources. Very long baseline interferometry networks worldwide coordinated to provide microarcsecond position measurements of 3I Atlas. This precision, achieved by combining signals from radio telescopes separated by continental distances, would enable trajectory predictions accurate enough for spacecraft intercept calculations. The Rubin Observatory's Legacy Survey of Space and Time, set to begin full operations in 2025, offered another advantage. LSST's wide-field surveys might detect future interstellar visitors earlier, giving us more lead time for mission planning. The lessons learned from the 3I Atlas encounter would inform rapid response protocols for subsequent visitors. The ethics of sample collection sparked intense debate in the scientific community. The Committee on Space Research, COSPAR, had set up planetary protection categories for different types of missions, but none addressed the possibility of sampling potentially artificial objects from other star systems. Was 3I Atlas a natural phenomenon that could be studied like any asteroid, or did it represent the property of another intelligence that should be approached with diplomatic rather than scientific protocols? The compromise was cautious. Sampling would be attempted only if 3I Atlas appeared to be shedding material naturally, or if the visitor provided some form of apparent consent through its communication patterns. Direct contact with the primary structure would be avoided unless absolutely necessary for the mission's success. International coordination went surprisingly well. The scale and timeline of the mission required resources that no single nation could provide quickly enough. NASA contributed launch services and mission operations experience. ESA provided proven propulsion systems and navigation software. Commercial partners supplied communications equipment and computational resources. The arrangement set a precedent for future international missions to unconventional targets. Contingency planning took up an enormous amount of effort. What if 3I Atlas changed course unexpectedly? What if it deployed defensive systems or debris fields? What if communication attempts provoked hostile responses? Each scenario required predefined responses that could be executed autonomously, since the 8-minute communication delay to mission control would make real-time intervention impossible. The encounter timeline was choreographed with military precision. Initial contact would happen at a distance of 10,000 kilometers, well outside any debris field, but close enough for detailed observation. The main spacecraft would maintain this standoff distance while deploying microprobes for closer inspection. Active communication attempts would start immediately, using every available frequency and modulation scheme. As the launch date approached in June 2026, public attention was intensely focused on the mission. Unlike previous interplanetary missions, which garnered modest public interest, the 3I Atlas rendezvous captured the global imagination. The spacecraft carried messages from world leaders, children's artwork selected through international competitions, and symbolic artifacts representing human civilization. The encounter itself would be brief but unprecedented. For 6 hours, we would get our closest look at visitors from another star system. The scientific return could answer fundamental questions about the nature of interstellar objects and the possibility of extraterrestrial intelligence. More importantly, the mission would demonstrate our ability to respond quickly to cosmic opportunities. But as the spacecraft sped toward its appointment with 3I Atlas, scientists braced for discoveries that might challenge every assumption about intelligence, technology, and our place among the stars. Part 9. Proof or Pareidolia, the Scientific Knife Edge. The most difficult aspect of extraordinary science is recognizing when you have found something extraordinary. Dr. Elena Martinez knew this as she examined the data returning from humanity's first interstellar rendezvous. The encounter with 3I Atlas had lasted 6 hours and 17 minutes, yielding terabytes of observations that would require months to analyze fully. But the initial findings created more questions than they answered, and the scientific community found itself on the razor's edge between discovery and delusion. Extraordinary claims require extraordinary evidence, a principle that had guided SETI research for decades. But how do you define extraordinary when dealing with phenomena that have never been observed before? The challenge was not just analyzing the data from 3I Atlas, it was creating entirely new frameworks for evaluating claims about non-human intelligence. The scientific method had developed sophisticated tools to avoid false positives. Pre-registered analyses required researchers to commit to specific hypotheses before looking at the data, preventing the unconscious cherry-picking that could turn noise into signals. Blind injections, fake signals inserted into datasets without the researcher's knowledge, tested whether detection algorithms could distinguish real phenomena from artifacts. Independent analysis pipelines, developed by different teams using different software, provided cross-validation for critical results. If 5 different groups working with the same data but independent methodologies arrived at the same conclusions, the findings gained credibility. If they disagreed, more work was needed. The competing models for 3I Atlas were grouped into 3 broad categories, each with its own predictive framework and observational tests. The engineered light sail hypothesis proposed that 3I Atlas was an artificial, possibly automated construct designed for interstellar communication or exploration. This model accounted for the object's extreme geometry, controlled rotation, thermal management, and radio emissions. It predicted that detailed analysis would uncover materials or structures inconsistent with natural formation processes. The exotic natural fragment hypothesis suggested that 3I Atlas was a previously unknown type of interstellar object, perhaps debris from a stellar collision or the disruption of a comet containing unusual materials. This model could potentially explain the object's anomalous properties without invoking artificial origins. It predicted that spectroscopic analysis would eventually reveal natural, if rare, formation mechanisms. The normal comet hypothesis maintained that 3I Atlas was fundamentally similar to 2I Borisov, with apparent anomalies resulting from observational artifacts, selection biases, or misunderstood natural processes. This model predicted that more detailed analysis would show conventional cometary behavior, masked by the object's unusual orientation and composition. Each model fared differently against the accumulating evidence. The radio emissions strongly supported artificial origins. Natural processes rarely produce narrowband signals with mathematical modulation patterns. The controlled rotation and thermal management also seemed more consistent with engineered systems than natural objects. But the spectroscopic data remained inconclusive. While 3I Atlas showed unusual surface chemistry, determining whether these materials were natural or artificial required understanding formation processes that might not exist anywhere else in the galaxy. Exotic did not necessarily mean artificial. The Encounter mission had provided crucial new data. Close-approach imaging revealed surface structures that appeared organized rather than random, patterns that suggested design rather than natural weathering or collision damage. But pareidolia, the tendency to see patterns where none exist, had deceived humans throughout history. The canals of Mars had seemed obviously artificial to 19th-century astronomers. Laser communication experiments during the encounter yielded the most tantalizing results. When the spacecraft sent structured light pulses toward 3I Atlas, the object's surface reflectivity changed in patterns that seemed to correspond to the transmission sequence. But optical effects in space environments could be complex, and confirming that the changes were responses rather than coincidences required statistical analysis that was still in progress. The historical context of Oumuamua provided both guidance and caution. That first interstellar visitor had shown non-gravitational accelerations that initially seemed inexplicable. Scientists proposed exotic explanations, fragments of alien technology, hydrogen icebergs, even suggestions that Oumuamua might be a light sail from another civilization. But careful analysis by Dr. Marco Micheli and his colleagues, published in Nature in 2018, demonstrated that the accelerations could be explained by conventional outgassing from a comet nucleus. The unusual geometry and lack of a visible coma had initially hidden Oumuamua's cometary nature, but detailed modeling showed that natural processes could account for all observed properties. The lesson was sobering. Extraordinary hypotheses should be the last resort, not the first. Natural explanations, even unlikely ones, deserved serious consideration before invoking extraterrestrial intelligence. II Borisov had offered a useful contrast, a clearly normal interstellar comet that behaved exactly as theory predicted. Its composition matched solar system comets, its outgassing followed standard models, and its trajectory showed no anomalies. Borisov demonstrated that most interstellar visitors would probably be unremarkable, making the apparent anomalies of 3I Atlas even more intriguing. The ongoing controversy over interstellar meteors added another layer of complexity to the analysis. The 2014 fireball, designated IM-1, had been classified as potentially interstellar based on its high velocity and unusual trajectory. Dr. Avi Loeb's expedition to recover material from the impact site had produced spherical fragments with compositions that some researchers claimed were artificial in origin. But the IM-1 spherules remained controversial. Other scientists argued that the unusual compositions could result from terrestrial contamination or normal meteoritic processes under extreme conditions. The need for larger samples and independent laboratory analysis had slowed progress towards definitive conclusions. These experiences informed the analysis of the 3I Atlas data. Every anomaly required multiple independent confirmations. Every unusual measurement needed to be reproduced by different instruments and analysis techniques. The scientific community was determined to avoid both false positives and false negatives, claims of alien contact that later proved wrong, or the dismissal of genuine phenomena due to excessive skepticism. Bias audits became a routine part of the analysis process. Teams of researchers would exchange datasets and analysis responsibilities, searching for systematic errors or unconscious assumptions that might skew the results. Adversarial collaborations brought together scientists with fundamentally different interpretations of the data, forcing them to identify the observations that might distinguish between competing hypotheses. The process was slow and sometimes frustrating, but it was effective. 6 months after the encounter, a preliminary consensus was emerging from the scientific community. The evidence for artificial origins was suggestive but not conclusive. Several key observations remained unexplained by natural processes, but the possibility of exotic natural phenomena could not be ruled out. The interim language for public communication was carefully calibrated. 3I Atlas exhibits properties that are difficult to explain through currently understood natural processes. While the possibility of artificial origins cannot be dismissed, more observations and analysis are needed to reach definitive conclusions. But even this cautious phrasing carried profound implications. For the first time in human history, the scientific community was seriously considering the possibility that we had encountered technology from another civilization. The burden of proof was enormous, but the potential discovery was worth the most rigorous investigation humanity could muster. The knife edge between proof and pareidolia remained sharp. But with each new analysis, each independent confirmation, each failed attempt to debunk the anomalies, the balance was slowly shifting toward a conclusion that would change everything we thought we knew about our place in the universe. Part 10. The message unfolds content, form, and meaning. What 3I Atlas was attempting to convey became evident only after months of meticulous analysis, and the message was both more intricate and more practical than anyone had anticipated. The communication was not a salutation or a philosophical treatise. It was an instruction manual. Dr. Yuki Tanaka at the Tokyo Institute of Technology headed the international decryption team. Her expertise in information theory and signal processing made her uniquely suited to tackle the layered structure of the visitor's transmissions. What at first seemed to be simple prime number sequences were revealed to be headers for more complex data packets, each one expanding on the mathematical concepts established in previous transmissions. The initial layer served as a mathematical foundation, establishing common concepts that would permit more sophisticated communication. Prime numbers led to algebraic relationships and then to geometric principles. The visitor was teaching us its mathematical language before trying to communicate more complex ideas. The second layer introduced physical constants. The fine structure constant, Planck's constant, the speed of light. But these were not merely confirmations of universal knowledge. They were presented with a precision that surpassed humanity's current measurements, suggesting our visitors had a more accurate grasp of fundamental physics. The third layer was where the message grew fascinating. The visitor started transmitting what could only be described as technical specifications, detailed instructions for building a radio beacon with capabilities far beyond current human technology. The specifications were elegant in their consideration of human limitations. Instead of assuming unlimited resources or advanced materials, the design utilized technologies that 21st century Earth could reasonably develop. The beacon would need a large array of precisely coordinated transmitters, but the individual components were within the reach of human engineering. More remarkably, the design included optimizations for Earth's specific rotation period and magnetic field characteristics. This was not a generic blueprint. It was customized for our world, indicating that the visitors had studied Earth's properties in detail before making contact. The fourth layer contained what Dr. Sarah Kim at MIT termed the network map, a description of how the proposed beacon would connect with what seemed to be a galaxy-wide communication system. The map displayed relay nodes situated at strategic points throughout local space, each one identified by precise astronomical coordinates. Some of these coordinates matched known stars. Others pointed to empty regions of space, where gravitational lensing effects might focus and amplify signals across interstellar distances. The visitor was describing a communication network that employed the galaxy's own structure as its infrastructure.